We capture enough solar energy on a cloudless day to power entire cities. Generating that electricity is a solved equation. The problem is keeping it. Sunlight hits the panels precisely when nature chooses. Civilization switches on the lights exactly when it chooses. That timing mismatch has created one of the most severe infrastructure bottlenecks of the 21st century. The current solution to that bottleneck is brute force. We are covering deserts with massive battery farms and rapidly multiplying gigafactories. Yet batteries solve only part of the equation because they strictly store power as electricity. They hold an electrical charge, but they cannot convert that power into a chemical fuel. Relying entirely on electrical storage forces civilization into an increasingly expensive, rigid physical footprint that consumes enormous amounts of land and raw materials. Every tree possesses a far more efficient alternative. Through natural photosynthesis, a leaf entirely bypasses electricity, taking sunlight and storing it directly as a transportable molecule. Modern civilization already runs entirely on this process. The coal and oil we extract today are simply ancient, fossilized sunlight, stored chemically over billions of years. The field of artificial photosynthesis attempts to engineer machines that do the exact same thing. The goal is to manufacture chemical fuel directly from atmospheric carbon dioxide and water, without waiting on geological timescales. The primary advantage is stability. Chemical molecules can sit in a tank indefinitely and ship globally on existing cargo vessels, avoiding the volatility of the electrical grid. Shifting our focus from generating electrons to manufacturing molecules would rewrite global energy infrastructure, directly solving the storage bottleneck. The barrier to building these machines is thermodynamic. In the real world, sunlight is never constant. Clouds pass and the intensity changes minute by minute. We can see the problem in this chart mapping solar intensity over a single day. The chaotic, fluctuating line is the actual sunlight. The flat, rigid line underneath is the precise, stable electrical condition that an electrochemical reactor needs to operate efficiently. When they do not match, the system crashes. To fix this, engineers added digital control systems. Look at the new data layer tracking a corrective algorithm. It is called maximum power point tracking. It constantly measures the voltage and artificially forces that rigid baseline to adjust thousands of times a second to match the solar input. But running those algorithms requires heavy hardware. The system suddenly needs supporting batteries, power converters, sensors, and external control electronics. This additive complexity drives up the cost of manufacturing. Every new component becomes a potential point of failure, severely restricting where these machines can be realistically deployed. The harder engineers worked to force stability onto the system using external electronics, the further they drifted from the elegant, self-regulating simplicity found inside a real leaf. Researchers at Osaka Metropolitan University took a radically different approach. They realized they could embed the control system directly within the physical material of the electrolyzer itself, stripping away the software completely. Every electrical system has a natural impedance, a measure of how strongly it resists the flow of current, and that resistance is highly sensitive to changes in heat. The Osaka team engineered a specific solid electrolyte to exploit this. This split-screen diagram illustrates the physical reaction. On the left, as the temperature gauge rises from the intensifying sunlight, you can see on the right how the internal resistance pathways physically widen, allowing a higher volume of electrons to flow through. It works automatically in reverse. Watch as the temperature gauge drops. The resistance pathways immediately constrict, restricting the electron flow. The fluctuating sunlight naturally warms and cools the reactor, perfectly matching the energy input. When the team tested this machine outside, it stabilized the electron flow perfectly under chaotic weather patterns. No sensors, no supporting batteries. The system continuously converted water and carbon dioxide into a stable liquid molecule called formic acid. By utilizing physical thermodynamics instead of digital software, they subtracted the fragile layers of complexity. They created a true, self-regulating artificial leaf. Formic acid operates as a liquid battery. It is raw solar energy, captured and locked safely inside molecular bonds. Manufacturing molecules addresses the hardest challenges in the energy sector. We need highly concentrated chemical fuels to generate industrial heat, bank power for entire seasons, and fuel international shipping. Pumping a liquid fuel through existing pipelines is vastly easier than the alternative. Expanding the physical electrical grid and building massive automated battery plants requires an enormous extraction of global resources. The Osaka architecture removes the converters and control boards entirely, drastically lowering the raw cost of building and deploying these molecular generators. This new model provides a realistic, scalable pathway to completely decarbonize heavy industry sectors that electricity simply cannot reach. The science still faces strict boundaries. Current artificial photosynthesis operates at efficiencies far too low to immediately replace mature industrial power systems. The chemical catalysts need greater longevity. The raw materials must become cheaper. The technology has to transition into a sprawling industrial facility. This is an arduous, iterative phase of refinement, but it perfectly mirrors the decades of trial and error required for early solar panels to drop in price and become globally viable. Scaling these materials would mean commercial buildings manufacturing their own liquid fuel on site, while global factories consume atmospheric carbon dioxide as their primary raw feedstock. After centuries of building increasingly complex digital infrastructure, we are slowly moving toward a fundamentally different system that operates directly through the embedded logic of plants, shifting the focus from managing electrons to mastering the physics of a leaf.